Hi everyone. In the next 20 minutes or so, we'll be talking about OAuth attacks under the emerging ecosystem of integration platforms. I'm Kaixuan, a PhD candidate at the Chinese University of Hong Kong. This is a joint work with Xianbo Wang, Professor Wenqian from my university, and Adonis Fung and Julien Lecomte from Samsung Research America. So integration platforms are all-in-one platforms that connects and aggregates the functionalities of diverse apps or services on the internet, and even Wi-Fi connected IoT devices. For example, you can ask the platform Alexa to turn off your smart bulbs and then get a ride with Lyft to the airport. But in this example, since you're communicating through Alexa, the Lyft server must somehow figure out which Lyft account is requesting the ride. So that's how account linking comes into play. Account linking is a must-have feature supported by all integration platforms. It links an end user's app account to their platform account, such that the platform can control the apps on behalf of the end user. To establish account linking, OAuth 2.0 is the most prevalent protocol being used. So back to the integration platform concept. In a narrow sense, people often refer to it as workflow automation platforms like Microsoft Power Automate and IFTTT. But here we're also including several other types of platforms that have a similar architecture. Based on their usage scenarios, this also includes virtual voice assistants like Alexa, as you've seen before, and Google Assistant, smart homes such as Google Home, and most recently, large language model platforms with plugin support such as ChatGPT plugins. Some people also refer to this kind of integration based on its development approach. So you may hear academics talking about trigger action platforms or the buzzword low-code, no-code platforms by people from industry. So another would the use case of account linking coincides with the traditional OAuth use case to grant authorizations. OAuth 2.0 is a three-leg protocol done in two phases. It's three-leg because there are three entities involved: an OAuth client, operated by the integration platform backend, the user agent, running the integration platform frontend, and the authorization server, which is operated by the integrated app servers. It's done in two phases. In the first phase is the authorization phase, which would issue a short-lived authorization code. To begin with, the end user would initiate account linking via the integration platform frontend, and then it would start the OAuth flow and hit the platform backend. And then the user would be redirected to the integrated app's authorization server. The user would then be asked to log in at the app's website and authorize the account linking. But although it is named authorize here, the authorize button or any user consent can usually be skipped if there's a prior consent. So this will make the authorization an automatic process, issuing the authorization code without any user interactions. So the authorization code would pass through the user agent and then be handed in to the platform backend. It would hit the redirection endpoint, labeled as R here, which is specified by the redirect URI parameter in the earlier request. And the second phase is the code exchange phase, where the authorization code is exchanged, is redeemed for an access token. And eventually, the access token indicating the app's account access would be associated with the user's platform account. And from now on, the platform could call the APIs with a token attached to control the app. So integration platforms often have an open marketplace that accommodate all its apps, and any third party can register and publish an app in the marketplace, and that's why it's considered an open ecosystem. Keep in mind that third-party apps could be inherently untrusted, and there could even be infiltration of malicious apps. So as an end user, you could already say something different when we talk about this integration platform architecture, which differs from the traditional OAuth use case. So when OAuth protocol is originally invented, it focuses on the use case where big name providers offer resources to the third parties. So usually there is an API or identity platform operated by vendors like Google, which acts as a provider. So either it will provide resources such as Google Drive access, functioning as an authorization server, or it's the IDP, the identity provider, that offers authentication for single sign-on. So the platform would issue access tokens to the OAuth clients, each operated by one third-party app. So because this paradigm is the more the most standard OAuth use case. The apps are often simply called OAuth apps. But in integration platforms, there's a paradigm shift where multiple apps can integrate at the platforms that's built by those big name providers. So platforms would implement the OAuth client, and since the apps would share their resources to the platform, the apps would play the role of authorization servers. So in this new paradigm, on the right-hand side, the third-party apps are integrating in these platforms, so they're often referred to as integrations or integrated apps. And recall that the platform usually offers an open marketplace where potentially untrusted or even malicious apps could be integrated with ease. So this would introduce malicious authorization server with ease. So next, I'll give some high-level ideas on how OAuth attacks under integration platforms could go wrong. How things could go wrong, so how the attacks will work. So at high level, normally it's the user that links his own app account, like Lyft account, to their own platform account, like Google Assistant account. So it's perfectly fine and nothing could go wrong. However, let's say I'm an attacker and you are the victim. If I can somehow steal your Lyft account and then bind it to my Google Assistant, then I can request a ride for free and you're going to pay my bill. So this will cause account takeovers, and this can be achieved with an attack called cross-app OAuth account takeover, or COAT. And on the other hand, if I as an attacker can unknowingly bind my Lyft account to your Google Assistant, then I can track or trace it whenever you request a ride with your Google Assistant. So this will cause privacy leakage. And it can be achieved with another attack called cross-app OAuth request forgery, or CORF. So in our research, we investigate these two attacks, COAT and CORF, that could either leak or inject an authorization code. So they're all based on the shared assumption that an attacker can set up a malicious app in the platform and the victim establishes OAuth with it. So the malicious app would target the victim's authorizations as a benign app. And that's why we call it cross-app OAuth attacks. And we have also provided countermeasures tailored for such attacks in integration platforms context. So this is a brief overview. And now let's dig into the details. The challenge here lies in the fact that integration platforms need to support multiple integrated apps, right? But maybe hundreds or thousands of them, where each app would have its own authorization servers. And by the way, we'll be using Alexa for illustration here. So Alexa is the platform. So the platform needs to support account linking with each of the apps individually in separate OAuth flows. So in order to achieve this, the platform must remember the user's choice of the app and later retrieve it. Why? Because as OAuth authorization code grant involves two phases, for the second phase, the code exchange phase, to work as expected, the platform needs to send the authorization code back to the exact same app that issues the code earlier. So to do this, the platform needs to first embed its initial contact in and later extract this information at the redirection endpoint and then conduct code exchange. So we call this process the active app tracking process, which is a basic functional requirement. There are two common patterns to do the active app tracking. One way is through the state parameter. The state parameter passes along the authorization phase, so when the state is generated, an app ID can be embedded therein, for example, as a JWT claim. Just so you know, the same information can also be tracked by other internal states of the platform, so it's not limited to the state parameter, but could also be, say, the platform session, or even a front-end managed in-memory state. So this information alone is adequate already to fulfill the functional needs of app tracking. However, it is insufficient from a security standpoint. Why is the case? Because the state parameter only reflects how the OAuth is started, but it cannot track how it ends up with. So because of the state is opaque to the authorization servers, it could have actually traveled through multiple authorization servers without the platform nor the apps noticing. So this oversight can result in an attack that renders account takeovers, which is called COAT, cross-evolved account takeover, and it goes like this. So first, when the victim stumbles upon a malicious app for account linking, the platform would embed the malicious app's ID in the state parameter and take the victim to the malicious app server. But instead of authorizing the user, the malicious app server would issue a crafted redirect to the benign app's authorization server. And from the benign app's perspective, everything looks legit, so the benign app would issue an authorization code. But the redirect would keep the malicious app state in the request, such that when the state is returned to the platform backend, together with the auth code, the platform would retrieve the active app information from the state and think that it has always been interacting with the malicious app. And therefore, it would leak the authorization code to the malicious app's token endpoint. And once the authorization code is leaked, that's endgame. The attacker just needs to launch a vanilla authorization code injection attack to redeem the code and then bind the victim's token to the attacker's own platform account. So because this is essentially stealing the victim's app account, we name the attack cross-evolved account takeover. So the second common design is to track the active app by the redirect URI. By embedding an app ID in redirect URI, like in the URL path, the platform could extract this information when the user agent hits the redirection endpoint. But this mechanism is flawed as well. The reason is that the redirect URI by itself, it has weak integrity, so it can be altered by an attacker with a malicious app. So in this setting, we could launch a different attack that enables privacy leakage, and we call it cross-evolved request forgery because it resembles login CSRF. The attacker also begins with the victim starting account linking with a malicious app, but because user URI has lacks integrity protection, the attacker could change the active app from malicious app to the benign app. And what's the purpose? It will make the platform later contact the benign app for code exchange. So the attacker could leverage this app context switch and inject a still valid authorization code of his own in. And that's how an attacker injects its own app account to be forcefully linked with the victim. So let's step back a little bit. So the root cause of both of the problems is that the platform solely relies on either state or whatever the URI for active app tracking. So to defend against both code and core attacks, the solution would be for the platform to embed a unique app ID in both state and the URI in both parameters, and then extract from both and ensure that their consistency before doing further code exchange. Why would it be an effective approach? Because now in the event of a code or core attack, the state parameter would indicate that of a malicious app's identifier, but the URI would indicate benign app. So this app ID mismatch would make the attack sensible by the platform. So yeah, mismatch detected. So this is actually an important security requirement, and at a high level, this will ensure that the app that starts OAuth would also end OAuth. So to scalably and precisely determine the susceptibility of a platform to cross-app vulnerabilities, we propose a decision tree-based testing approach. The high-level idea is that it will go through the OAuth flows of the two different apps, inspect the traffic, and then swap the OAuth parameters at the redirection endpoint in different ways. So this is to proactively introduce app ID confusion into the OAuth flows, and then we'll inspect the OAuth outcome to see if an authorization code can actually be successfully redeemed. So the key benefit of this approach is that it can derive concrete conclusion on the security or insecurity of a platform without actually relying on integrating a malicious app and then launching extra attacks, or knowing internals about the platform. It means that like even as a user, you can also test out you can already test out like whether the platform you're using on a daily basis is insecure or secure. So based on this approach, we designed CoveScan, a semi-automated dynamic testing tool for vulnerability discovery. And it takes at most 3 OAuth flows to derive a concrete conclusion for a platform. So as for evaluation, we investigated 24 platforms in total and narrowed down the scope to 18 of them with an open marketplace. So this includes 6 workflow automation platforms and the 6 workflow voice assistants, 4 smart homes, and 2 large language models with plugins. And we found 16 out of the 18 platforms vulnerable, including big names such as those from Google, Microsoft, Amazon, and Samsung. So 9 platforms support attacks that can be completed in 1 click, combining other flaws like CSRF. And moreover, we found that like the tool CoveScan can precisely assess the platform's security or insecurity. As a highlight, our code, the cross-app wall that got takeover vulnerability with Microsoft, is a one-click attack that received a CVE with CVSS score of 9.6. So next, let's move on to some FAQs. So some may ask, like, isn't the OAuth extension PXE or PKCE supposed to solve the problem? The short answer is no. Indeed, PXE is generally considered as effective in mitigating authorization code injection attacks and can be an alternative defense to CSRF attacks in OAuth. But as a malicious app, it can bypass PXE. It's not by like exploiting implementation flaws like PXE downgrade attacks, you may see it somewhere, but invalidating the protection provided by PXE at the protocol level, at the spec level by following these concrete steps. And the second FAQ is, isn't it just mix-up attacks? Well, long story short, our cross-app OAuth attacks can be considered as practical variants of mix-up attacks. So first, a brief review of history. Initial discoveries of mix-up or IDP mix-up attacks can date back to around 2016, where 2 groups of researchers first discovered that there could be such an attack in theory. The community discussion has led to the defenses in 2 RFCs. But compared with mix-up attacks, our cross-app OAuth attacks target different scenarios, which eases the attack assumption and boasts a more practical attack. Moreover, we claim that like the existing mix-up defenses are impractical for this integration platform scenario. Namely, it's difficult for the platforms to actually apply the defenses. So next, let's break down the 2 claims. So usually when people talk about mix-up attacks, people always use the traditional paradigm, which we showed on the left-hand side. So the most practical scenario where there are multiple authorization servers involved in the traditional paradigm is single sign-on, because most websites support more than 1 IDPs. But the thing is, the second precondition for the mix-up attack to work is that there must be a malicious authorization server out there. And this precondition is really hard to satisfy in practice, because you just cannot expect that trusted entities like Google to be hacked, or like a website like Spotify suddenly supports logging into an attacker control IDP out of nowhere without prior trust. But if we look at the right-hand side, in integration platforms, since it's an open ecosystem by design, so untrusted authorization servers could integrate a malicious app to get involved with these. So that's how mix-up attacks could turn from a theoretical attack to a practical attack. And similar situations apply to Corv. And another FAQ is like, why can't we simply apply existing mix-up defenses to integration platforms? And the short answer is they don't automatically or magically fit into the integration platform's use cases. So the existing mix-up defenses rely on the concept of an authorization server issuer, or issuer for short. It is a unique identifier for each authorization server. However, because of the open marketplace setting in integration platforms, issuers are no longer unique to the platform. because two apps could actually share the same issuer. For example, here you can see there could be an official Dropbox app that supports like uploading and downloading files with these two official APIs. But any third-party developer could also publish a custom Dropbox integration in the marketplace that performs some other operations, also leveraging the sub-official APIs by Dropbox. So as you can see, like these apps will share the same authorization server, but technically they are two separate entities and should handle OAuth independently. So to summarize, we suggest the tailored spec change for integration platforms to be built upon the concept of an app ID. So this is an alternative defense that would like the app ID would embed in the reader URI during the pre-registration and also OAuth flows. So we highlight that for like both functional and security needs of active app tracking, I should use this app-specific identifier, which is a more suitable identifier than the issuer, which is like an authorization service specific identifier. And moreover, like this defense turns out to be a robust countermeasure that kills two birds with one stone, so it mitigates both code and port attack. So to contribute to the community, we published an IETF draft to propose changes to the OAuth security best current practice, and you can find them in this link. We'd like to conclude our talks with these key takeaways. So first and foremost, as open ecosystem, the context of integration platform enables practical cross-app OAuth attacks that could lead to account takeovers or forced account linking. And the way it's practical is by introducing malicious app integrations, introducing malicious authorization servers based on these app integrations. And secondly, existing RFCs provide authorization-specific issuer-based defense, but the defense lack an app-specific perspective, which is a tailored security boundary for multi-app integrations. And third, with more than 15 mainstream platforms identified as vulnerable, and each hosting hundreds or thousands of apps, our attacks achieved pervasive impact across the internet. And we also developed CoveScan. It's a decision tree-based testing tool to ease the vulnerability detection burden. And we also published an IETF draft to raise awareness of the attack scenario and tailored defense in the broader community. That's all for my talk. Hope you enjoyed it. And feel free to scan this QR code to learn more. Thank you.